All right, so we're going to talk about chemical bonding. And to start chemical bonding, we're going to first learn about the periodic table, its development, its history, most importantly, though, how we're going to use it. So way back in 1860, there were 60 known elements. And the reason that 1860 is an important date is because that is the point where we learned about relative atomic masses. So it was the first time that they were able to say, okay, hydrogen, we're going to say that it has a mass of 1, and carbon is 12 times heavier, so its mass is 12. So of course, we're not putting them on a scale and weighing them because they're too small, but we can at least say that how many times greater they are in mass than hydrogen, for example. And then about 9 years later, so we have these masses of elements, and again, we only know about 60 of them, so about half of what we have today. A Russian scientist and professor named Dmitry Mendeleev came along and created the first periodic table. He actually did it over the course of one weekend. He had the idea for a while, but he had to finish his textbook that he was going to use for his class and send it to the publisher on Monday. And he still didn't know quite how he was going to organize the elements into one cohesive table that made sense. And he came up with it over the weekend. He was playing, legend has it, he was playing solitaire, had the cards with the elements, properties on them laid out, and it kind of struck him that if you put the elements in order of their masses, you see these periodically recurring traits. And so he uses this thing that we call the periodic law to create the first periodic table. And the periodic law simply says that properties of an element are a periodic function of atomic size. So instead of just being a function, they are a periodic function. So if you put them in order by size, starting with the smallest element, then every 8 or so elements, depending on the property you're looking at, you'll see the properties repeat themselves. And so we call it a periodic function. Sometimes you'll hear the term periodicity, and that's essentially just a synonym for periodic law. Okay, so some important things about Mendeleev's periodic table. It was very important that we understand he was able to use it to predict some elements that hadn't been discovered yet because of where they sat in the periodic table. If there's an open space, he could look at the properties of the elements around that element that hadn't been discovered yet and predict what properties they might have. Now, his was unique from ours, or different from ours, because they didn't know about protons in 1869. They just knew about atomic masses. And so his was in order of atomic mass, not atomic number, which didn't happen until Henry Moseley was the first one to propose an atomic number from protons in 1911. His was also different because his groups or families, which we'll talk about more in a second here, actually go horizontally. So when you see the modern one, you'll see those families run vertically. So for example, the halogens or the alkali earth metals, the alkali metals or the alkaline earth metals, those are families, and they run vertically on the modern periodic table. He also had no noble gases, which kind of makes sense if you think about it, because a noble gas is an element that doesn't react with anything, or at least not very readily, very often. And so it kind of makes sense, hopefully, that he wouldn't have known about them, or that it took a while for them to be discovered, because unlike oxygen or nitrogen or hydrogen, they don't really interact with other elements, and so it makes them a little bit harder to detect. Here is a copy, I believe the top there is in German, but this is a very early copy of Mendeleev's periodic table. You can see some interesting things here. He's got some blank spaces, like this element with a mass of 45. These two elements here, 68 and 70. And again, these are not proton numbers, these are mass numbers. But he was still able to figure out what family they belonged in, right? So like carbon and silicon were in the same family, because remember, his families ran horizontally. And then there was a missing element, which he thought would have a mass of about 70. And then in the same family, we had 10, SN, which has a mass of 118. So he's predicting that someday we're going to have a mass here I'm sorry, we're going to have an element here, and that its mass will be about 70, and it'll probably share some characteristics with carbon, silicon, and tin. And as it turned out, he was right, and it was germanium, which has since been discovered. The same thing with gallium. Um, we watched the TED Ed video about this, but gallium has common properties with boron and aluminum, and he was able to predict those properties. Now, he didn't get them all right. Not, for example, he had gold in the same family as aluminum and gallium and boron, but it's not in the same family today. So he didn't get it quite right because, there was simply, with about half as many elements to work with, you can imagine it was a tougher job. But he actually did a very good job of putting a lot of these in the correct families. Okay, so the modern periodic table are groups or families run up and down vertically, and they are numbered 1 through 18. So if you have your purple periodic table handy, you might get that out and take a look. There are 18 vertical columns. A couple different ways we can arrange this or look at it. The main groups or the representative elements are the S and P blocks. So groups 1, 2, and 13 through 18. So again, the 1 and 2 are the S block, 13 through 18 are the P block. Then we have the transition metals, and those are the D block, essentially, groups 3 through 12. Although we'll talk a little bit later, some of the lower left part of the P block are also considered transition metals, like lead and tin. And then the F block at the bottom of the chart, those don't have group numbers, but they're still there, and sometimes they're referred to as lanthanides and actinides. Sometimes they're called inner transition metals. There's a couple different ways we can refer to them. But those are an important group as well. Another thing on the modern periodic table we pay attention to is while our vertical columns are called groups or families, our horizontal rows are going to be referred to as periods. So if you remember graphing your data from the all in the cards activity, you saw data that either constantly went up for a while before going back down, or it constantly went down for a while before jumping back up. Well, what you were looking at there for those elements that were, for example, going up and up and up and up, those were elements within the same period. And the same thing if you had a property where they were all kind of going down. Okay, so let's talk about some important groups. You can mark where these are if you want to on your own periodic table, like on your purple handout periodic table that I gave you. The easiest way to tell the metals, nonmetals, and metalloids is if you will just mark where the metalloids are. And you can maybe, I don't know, pick a color, a highlighter, shade it with your pencil, whatever you want to do. Essentially, if you'll notice on this periodic table, you have this key down here that tells you that the purple are the metalloids. And we'll talk about what that means in a second. But if you can identify the metalloids and maybe shade them in on your periodic table so you know where they're at, they kind of make a diagonal line through the P block, okay? But those are the metalloids. And the reason I say that those would be the most important thing to know is once you know where the metalloids are, everything to the right is a nonmetal, and everything to the left is a metal, with the exception of hydrogen, which is sort of on its own over here. That hydrogen is a nonmetal that's on the left side of the periodic table. So if you want to mark up your periodic table, you can, or if you just remember that the metalloids roughly make a line from boron down to the right, and that everything to the left is a metal and everything to the right is a nonmetal. Okay, so the metals are in green here, you can see that. They are malleable, and if you don't know what malleable means, you might want to write down a definition, but malleable essentially means that you can change its shape without it shattering, okay? So in other words, it's not brittle. If you take a piece of copper and you hit it with a hammer, at least at first, it's going to flatten. It's not going to shatter, right? Whereas glass or a ceramic pot or something like that is going to be brittle, which is the opposite of malleable. Ductile is like malleable, only it specifically refers to being able to be stretched or drawn into a wire. So that's what ductile means, and metals are ductile. Conductive, and when we say metals are conductive, we mean they're conductive of heat. Usually also electricity. So most metals are pretty conductive. They're not all conductive to the same extent though. Then we have the metalloids. The metalloids are kind of like the intermediate step between the nonmetals and the metals. So like silicon, for example, is a semiconductor. Silicon is element number 14, right? So silicon is a semiconductor, so it's also shiny like a metal, but it's kind of brittle like a nonmetal, so it has intermediate properties, right? So those are our metalloids. They sit physically, geographically in between metals and nonmetals, and they also have kind of in-between properties. And then finally, we have the nonmetals, and the nonmetals, most of them are gases. So like the noble gases, of course, but also fluorine and chlorine and oxygen and nitrogen and hydrogen. Those are all gases. And there are a couple solids, carbon, phosphorus, sulfur, selenium. Those are all solids. So is iodine. But for the most part, if it's a gas, well, definitely if it's a gas, it's a non-metal. We know that for sure. But if it's in the solid form, you should find usually that it's going to be non-conductive, dull, in other words, not shiny, and brittle rather than malleable. So if you imagine like the graphite from your pencil, that's made of carbon, which is a non-metal. So it's not especially shiny. It is brittle. It is actually a little conductive. Carbon's kind of unique that way, but most non-metals are not conductive. Okay, we're going to talk real quickly here about a couple of important groups. The left side of the periodic table, group number 1 from lithium and below. So notice we're not including hydrogen, even though it is technically in group 1. These are alkali metals. So they're metals, but they're very soft, all right? They are not found in nature in elemental form, and the reason for that, if you look below, is they are very reactive. These are metals that will actually catch fire and possibly explode if you drop them into water, which of course we're going to do. So you can see that happen. But alkali metals are very, very reactive. And we'll talk about why that is in terms of the atom itself later on. Then we come to group 2, which are the alkaline earth metals. They're basically just like a less extreme version of the alkali metals. They're a little bit harder, they're not quite as soft. They're still pretty reactive, but not as reactive. So for example, magnesium burns really well, but if you drop it in water, it doesn't do a whole lot. It's not very exciting. So those are the alkaline earth metals. Then we're going to jump all the way across the periodic table to the halogens. The halogens are named halogen because it means salt producing. You find them in a lot of salts. They react with metals to form salts. They're very reactive too as well. So they're nonmetals. They're pretty much the most reactive nonmetals, where the alkaline earth metals are the the alkali metals are the most reactive metals. The halogens are the most reactive nonmetals. So fluorine, chlorine, bromine, iodine, and astatine, those guys are so reactive that if you do have a sample, let's say of chlorine, you're never going to have a single atom of chlorine. It's going to be Cl2, right? And even after it bonds to make Cl2, it's still actually extremely reactive. All right, and then finally we have group 18, which are the noble gases. The noble gases are interesting because they don't react. They're very unreactive, and they do exist as single atoms. So, if you're looking at a helium balloon, you've got a bunch of single helium atoms just bouncing off of each other and bouncing off of the inside walls of that balloon. They don't have any color. They don't react. They don't tend to smell like anything. They're very inert. So we call them the noble gases because they don't sort of associate with other elements. They separate themselves from the rest of the crowd. All right, and those are important groups. And we'll talk about why some of these properties exist as we get into part 2, which will be our periodic trends.